think this is good? Okay. So as you can see, history of liquid metal batteries. And what I wanted to do today is, rather than give you a electrochemistry lesson, is to give you a sense of how we arrived at this. What was the path that we went on? So let's look at the starting point. And so I thought about why we were inventing this, because people were very keen on lithium ion. And to this day, there's this misunderstanding of the utility of lithium ion, which was really invented for handheld devices. It was never intended for massive stationary storage. Even though people put it in such applications, it's suboptimal. So what are the specifications? Long service lifetime, not 3 years, not 5 years, but decades, not years. So that was number one. Second one was it has to be safe, fire resistant. You know, if a handheld device catches fire, it's a bad day. But if you have a 100 megawatt hour facility catches fire, we saw in California last month, they closed the Pacific Highway. Pacific Coast Highway was closed not because of flames, but because of fumes. The fumes from lithium ion fire will kill you. You'll never burn, you'll die from the fumes. So that's, I suppose, a blessing. And it has to be operationally flexible. It has to be able to do fast response for things like frequency regulation, voltage stabilization, and then it has to go for long duration. So it has to be both sprinter and marathoner. The battery that powers the hearing aid doesn't power the automobile, but this thing has to do everything. And finally, it has to go to super low price point. It's not battery versus battery. It's battery displacing gas or diesel. And you have hydrocarbons, which are deeply entrenched and heavily subsidized. So you have to be really, really smart to invent in this sector. And it has to be all of them. If I just had the top three, long service, lifetime, safe, operationally flexible, I could have given you that battery 15 years ago, but it would have come in at a NASA price point. It has to come in cheap. It has to be cheaper. By the way, I totally reject the notion of green premium. When people tell me this is a new technology and it's green, but it costs more, the price of electricity is going to go up, the price of steel is going to go up, I say, this is a failed technology. Fix it. We have an opportunity to reinvent our world, and we should be doing so in a way that is more efficient and comes in at lower price. So I set that as the bar. Otherwise, if we give low expectations, we'll meet low expectations. So I say, everybody, high expectations. All right, so how am I going to do this? So at the university, I said the university paradigm for research is wrong for this. What's the university paradigm? It's invent the coolest chemistry, publish in the highest tier journals, and maybe there's a startup company in there someplace. And then the people at the startup company will chase down the cost curve. And they will, but they won't get low enough, not in this market. You have to think about cost on day one, not day 10,001. So I said cost-informed discovery. That means you think about cost at the pre-competitive early stage when you're doing the basic exploratory work. And then you've got a likelihood of hitting the price point at the end. Nobody wants a gorgeous, expensive battery. I could build you a gorgeous battery out of lithium and tellurium, but tellurium is about as earth abundant as gold, so it's not going to scale. By the way, I'm a truth teller. I didn't come here to offend, but when I look at people working on telluride solar cells, the first thing I do is say, earth abundant as gold, and you want to make something that it will not scale. So let's think about how we're going to change the world. So we had to do something different. So I don't know why this isn't displaying. All right, so what's my path? I don't know, there's something at the top that's missing, but don't worry about it. Confine chemistry to earth abundant elements, all right? So I say if you want to make something dirt cheap, you should make it out of dirt. And preferably dirt that's locally sourced. Because I was writing this already 10 years ago. Nobody was thinking about supply chains. I said, we want dirt that's locally sourced. Otherwise, why would you trade your dependence on imported petroleum for dependence on imported neodymium? That's stupid. And yet we do it because, oh, the winds and so on. All those electric cars, what do you think the magnets in those motors is made of? And where's that neodymium coming from? You know, it's not that scarce, but it's maldistributed. So I talk about not only earth abundance, but distribution. If you have something that's earth abundant, but it's all found in one place, and that place is an unsavory place to do business with, then you're now in a trap. And I think about manufacturing. Why do they call a lithium-ion battery factory the gigafactory? Because it costs $5 gigadollars to build the thing. It is ridiculous. So I don't want a gigafactory. I want a factory that you can build easily. So I think about the design at the earliest stage. So this is the thing. Pose the right question. You see at the top, I say, inventing a colossal cheap storage device. You don't see the word battery in that phrase. Because if you say battery, you bias your mind. You start thinking about something that's a right circular cylinder. And I don't want that. I just want a colossal cheap storage device. I don't care about the format. Huh? So it's pose the right question. If you ask the wrong question and you get the brilliant answer to the wrong question, where are you? So, by the way, disregard the experts. I did not speak to any battery experts because battery experts, they're some of the most dour downers that you can ever meet. They would tell you everything that you propose. It can't work, it's already been tried, this is stupid, and so on and so forth. So I didn't listen to any of them. In fact, I would almost say, ask them for their advice and then do the polar opposite. You're probably on a good track. And so up until this time, I was working on electrometallurgy. That's how come I knew something about molten salts and liquid metals. Because I was working on aluminum, magnesium, titanium, the alkali metals, and so on. And so this is a modern aluminum smelter. This is Alouette in Quebec. This is probably about 30 meters from left to right. Probably goes back about 2 kilometers. And this is cell after cell. This facility is probably 500,000 amperes at 4 volts. That's 2 gigawatts continuously. And continuously producing liquid aluminum from aluminum oxide, and there's a molten salt solvent. And I looked at this thing and I said, wow, we can go from dirt to metal for less than $1 per kilogram. You go to the supermarket and look through all the meats, the poultry, the fish, the vegetables. You show me anything that you can buy for less than $1 per kilogram. There's not much there. And yet we can bring aluminum oxide from halfway around the world and turn it into liquid metal and then make it into a beverage container, $1 per kilogram. That's an economic miracle of modern electrometallurgy. So I looked at this thing and I said, if I could teach this thing not to consume electricity, but to store electricity and give it back on demand, I know at the end I'm going to have something that's big and cheap and traffics in huge amounts of electricity. My colleagues take the battery in this device and try to imagine how to make it big enough to fill this room. And we'll see who gets there first. But it's about posing the right question, the contrarian thinking. So this is the invention of liquid metal battery. This is a very early stage. This is a very old diagram. And so what you see here is that you have liquid magnesium on the top, liquid antimony on the bottom, and molten salt electrolyte in between. The liquid metals are insoluble in the molten salt, and the molten salt is insoluble in the liquid metal. So they lie on top of one another, just the same way salad oil and vinegar. There's no membranes, there's no separators, and then it's very easy to construct. So these are earth abundant and easy to build. And this is the paper, first paper ended up in Journal of American Chemical Society, and just to show the thing. Now, the design of molten salt, I just want to give you a little flavor of how we did it. It was not just cook and look. There was actually some science behind this. And so this is the Ellingham diagram for chlorides. And so we're going to use magnesium chloride as the molten salt because the magnesium is going to, it's the itinerant ion. So I need magnesium chloride as one of the constituents. And so this shows you, and for some reason my pointer doesn't work, but this will show you, I'm afraid to touch this too. So where the blue line intersects the red line, that's the free energy of formation of magnesium chloride at 800 degrees Kelvin. Okay? So I was figuring about 500 Celsius. So anything that lies below that line is okay. So actually I could, Peter brought out this big, there. You see, in the end, this triumphs over everything. So this, anything below this will be stabler than magnesium chloride, because we don't want, when we charge the battery, to plate out anything except magnesium. So that's the design. You start with magnesium chloride, and then you go from there. All right, so these are some of the other ones. So this is about minus 120 kilojoules per mole at 800. So here's 800 over here, and you can see way down here we have sodium chloride, potassium chloride. So those could be supporting electrolyte solvents, and we can keep going. There's a whole bunch of others. There's lithium chloride down here. If you want to build a really expensive battery, there's yttrium chloride, but we won't use this one. All right, so this is how we think about it. And then there's barium chloride and strontium chloride, but we want to make sure that we don't invert the three liquids. But there's room for maneuvering here in the design. So on discharge, the magnesium wants to alloy with the antimony, because the magnesium antimony alloy has a negative free energy. But I just told you that magnesium will not dissolve in the electrolyte. But magnesium is smart. Magnesium knows that if magnesium becomes a magnesium ion, the magnesium ion can traverse the electrolyte. And in becoming magnesium ion, these two electrons go through the external circuit and power our devices. And then as the magnesium traverses the electrolyte, it generates heat. And this is the threat to a lithium-ion battery. For us, that is an asset. We trap that heat. And so as the battery discharges, it gives off heat. And that keeps the battery at temperature. We have to heat it up once to melt everything. And then after that, as it discharges, it gives off heat. And then when we want to charge the battery, we force current through the system. And now, because of the relative stability of magnesium and antimony, magnesium is the one that is electro-refined out of the antimony and traverses, and then we restore the magnesium layer on the top and giving the battery its pristine initial condition, because we're purifying the antimony, we're purifying the molten salt, and we're making high purity magnesium on the top. And we're generating joule heat again. And so by discharge, generate joule heat, wait. Then charge, generate joule heat, idle. That daily cycling gives us enough heat to keep the battery at temperature just by operation. This is designed to be used. I don't know why people want a battery that isn't going to be used. You have all these people talking about long duration storage. They think they're going to store electricity from the sun and discharge it in the winter. This is completely stupid. The capital cost of that thing would have to be $1 per kilowatt hour. This is impossible. This is completely stupid. Don't be fooled by those things. You want the battery that's working, as was said at the beginning, about with the solar coming online every night. Surprise, the sun sets. And so we need the battery to get us through the night, every night. And we came to the realization that we started with magnesium antimony, but we could use a range of choices. So I call it a platform technology. So all these elements up in the northwest part of the periodic table, the most electropositive elements are for the negative electrode. You see, I never used the word anode. This is incorrect. This is not the anode. It's the anode on discharge. When you charge, it's the cathode. That's why the battery people never use the term anode or cathode. But this electrode, which is the anode on discharge, and the cathode on charge, is always polarized negatively. So they refer to it as the negative electrode, or they just call it the negative. All right? So the negative could be any of these. Could be magnesium. We've worked with lithium. We did some work with sodium. And now we're working with calcium. Could be any of these. And then same thing for the other electrode. I showed you antimony. We work with antimony. We work with lead. We work with bismuth. We could work with tin. We could work with zinc. So there's a plurality of options. And it would depend upon your local conditions, because I want the liquid metal battery to go global by being built locally. So batteries in America should be built in America by Americans using only American resources. No China, no Congo, everything done in England. Batteries in Europe should be built in Europe by Europeans using European resources. That way, Europeans become the authors of their own future. We don't drop in something that came out of China. I refuse that. And if we don't imagine that, we will just keep buying stuff that's made in China. So this gives us new possibilities, and the salts, of course. So I talked about don't talk to the battery experts. And when I hired on my students, I didn't hire on battery people. There's 20 people in this image. There's myself. Axiomatically, this picture must have been taken when I was younger. If you took the picture of me 20 minutes ago, I was younger when you took the picture. But this is about 10 years ago. And this is David Bradwell, who was my first student. He and I were both born in Toronto, in different years, of course, but we were both born in Toronto. And this is Louis Ortiz. And apart from the three of us, most of the people in this diagram knew no electrochemistry, knew nothing about molten salts or liquid metals. But they were bright. Obviously, they got to MIT. They were bright. And they were ambitious, and they're young, and they're full of idealism. And why they want to work for me? Higher sense of purpose. All they want to do is change the world. That's all. And so you harness that idealism, and they're fearless intellectually. They didn't know what was impossible. So I say the anti-experts. They're fantastic. And multinational forces, Korea, China, France, Trinidad. This is from Catalonia. Let's see. Oh, I bet you won't guess this one. Tahiti. Brice was from Tahiti, did his PhD at Sarcelles in Paris, and then came to me working, being paid by Total. And there were a few Americans I hired, tokens, you know, but that's the whole thing. All right, so, so now what's the progress report? Let's see. So we've, over the years, between 1,000 and 2,000 cells, many different chemistries, different combinations of salts, liquid metals and alloys and so on, and many of them below $50 per kilowatt hour for the electrodes and the electrolyte. And that's sort of, the $100 per kilowatt hour is sort of the big barrier. If you can get below that, then a whole bunch of other things open up possibly. So then David and Louis came to me and said, it's time to start a company. And I did not want, I'm being honest with you, I did not want to get involved in a startup company because I'm from Canada. I'm very prim and proper. I was a really strict academic, taught dutifully and so on. And I thought, startup, all this stuff is corrupting. I don't want to be involved in all this money and all this. I see so many colleagues. They're just totally blurring the distinctions between campus and off-campus, corrupting. It's just disgusting. I said, I don't want to have anything to do with that. But these guys were smart. They came to me and said, Sadoway, you talk about science and service to society. How are you going to get that battery out there if all you do is publish? You have to get the technology out there. So I say, okay, I agree with you, we'll do it. And so we started the company in 2010, and all the catchy names were taken. So we called it the Liquid Metal Battery Corporation. Terrible name, but it started anyways. And then a couple of years later, we changed the name to Ambry. I'd heard that, perhaps you know of this company, Cisco Systems. They make routers and things like this. And somebody told me that Cisco Systems got its name because it was founded in San Francisco. I said, I invented the battery in Cambridge, the other Cambridge, in Cambridge, Massachusetts. And I said, well, let's look at the name Cambridge. So I looked at the name Cambridge, and I took the front and back off, and there's Ambry, and Ambry.com was still available. And I said, that's an omen. You can't have a 5-letter name that's pronounceable in 2012 that hasn't already been taken. So we said, we changed the name to Ambry. And our Series A funding came from Bill Gates. I told you, I'm from Canada. I'm too polite. I wouldn't go to Bill. Bill came to me. Why would Bill come to me? Because I was teaching a big general chemistry class, which went on the internet starting around 2005. I had about at the peak, I had 630 students in this class. general chemistry, not advanced. All my colleagues, they want to teach DFT, all this other stuff. No, I want to teach the fundamentals, largely to first-year students. Elements of electronic structure and bonding. And the class was too big to fit in any auditorium at MIT, so they recorded the lectures, video recorded, and started posting them on the internet. And eventually, this facility, MIT OpenCourseWare, started by a couple of electrical engineers, went to the president of MIT, said, we have an idea. Let's put everything that MIT teaches on the internet for free. And he said, what? Yeah, for free, let's do it. And a whole bunch of us said, we're in. And so they took video recordings of my lectures and posted everything. Somehow Bill started watching these. And Bill was very interested in what I was doing. And so it was in August of 2009. I got an email from a woman who said she was his executive assistant. He was coming to Boston on 25th of September. Would I have 90 minutes to meet with him? Well, I ignored the email. I thought the students had hacked into my account. I said, I'm smarter than that. You're not going to make a fool out of me. So I didn't answer the email. And she wrote again and said, maybe you didn't see the email, but Mr. Gates really wants to see you. I showed it to my colleagues, and some of them said, I think it's real. So, okay, so I wrote her back and said, okay, what's this all about? And finally I said, you give me some more details. And then he jumps in, and he was very methodical and so on. So we sat 90 minutes. I taught my class that day. We sat for 90 minutes, and towards the end, he said, what are you working on? And I had no results. I sketched the idea of the liquid metal battery out on my whiteboard in my office. And he said, if you ever decide to spin that out, let me know. I'd be willing to put some money into it. So I met Bill Gates, not because I wrote a piece for the Financial Times or for the Wall Street Journal. I met Bill Gates because I was teaching a first-year chemistry class. It's a story you can tell in mixed company. So Bill was our first investor, and then the French energy giant Total was also investing in some research at MIT, and they matched him, and that's how we got our start. So there's all kinds of things I can go into, but just a few that are noteworthy. We'd moved from magnesium antimony to lithium lead antimony, and this is the fade rate. And what does that mean? It means that we have some cells at Ambry, this is going back a number of years, that were running for 4.5 years at temperature. And I had conversations with some of you about the corrosion and stuff. These things are running 4.5 years, still cycling, and they're running about 500 degrees Celsius. And deep discharge, full discharge, 5,000 cycles. If you did that once a day, every day, 5,000 days would get you to 13 years. 13 years. And this is the chart. This is after 4,000 cycles, and it's still retaining 99.5% of nameplate capacity. If I put lithium ion on here, by about 2,500 cycles, it would be down, way down. And by the way, suppose you lose 20% of capacity. Suppose you're at 80% of capacity. If it's stationary storage, you need the full capacity. Either that, or you have to buy more capacity. Or you have to oversize your initial purchase in anticipation of the capacity fade. We don't have capacity fade. But this is really problem. We'll talk tomorrow more about the economics and upscaling, but I had to show you this one because this is data from history. In 2010, it was about $1,000 per kilowatt hour for lithium ion. And these are data points as you're going down. And so these Barbie dolls at Bloomberg New Energy Finance fit these data to a semi-logarithmic plot and then projected it out. And the slope on the semi-logarithmic plot is 0.19. And so they declare a 19% rate of learning. I don't know where you get, I guess this is I never went to business school, mercifully. But anyways, this is the stuff. So they're projecting out here by 2030 it'd be $73 a kilowatt hour, which is less than the cost of the components. If I told you, I'm going to give you wine that's going to cost less than the cost of grapes, you'd say, I don't believe that. But that's where we are here. But anyways, people looked at this, and this is the fit that they did. And so what happens? We started with lithium lead antimony when lithium ion, we were shooting for about $270 per kilowatt hour when lithium ion was way up here. Well, by about 2014, lithium ion is crashing down below 400. And with these projections, our investors come to us and say, you guys are toast. You're in deep trouble. So we had to migrate. First of all, we had the lithium lead antimony. By the way, this was the paper, letter in Nature, where we made the discovery that the voltage between lithium and lead, which is very low, but lead is low temperature, low melting. Lithium antimony is high voltage, but high melting. So we put lead and lithium, lead and antimony together. And we figured the voltage would be some kind of like a mean between the voltage of each of them. It didn't work that way. It was a pleasant surprise. I should have anticipated this, but this was a surprise. When the lithium goes into lead antimony, it preferentially bonds to antimony, and we get the high voltage of lithium antimony and the low temperature of lithium lead. That was the discovery, and that opened our eyes to all sorts of alloying that we could use without, because the temperature is set by the melting points. We want to get a lower operating temperature. It's just so many discoveries. That's what's depicted in here. All right, so then we moved to lithium bismuth, which is fantastic, but bismuth was far too expensive, and then there was a new mine opened up in Vietnam. And so then we were able to afford to go to lithium bismuth, and we went down lower. So a lot of what we learned was applicable, but there's still trouble. So many new things to learn. And so this one was published in Journal of Power Sources. And then finally, the price continued to drop, and we got really angry and decided, all right, let's go to calcium antimony. And calcium antimony is way down here. They'll never catch us with this one. And all this stuff was backed up with when you see some of these battery companies, they never announce no publications, no patents, and no disclosure of what their company is doing. To me, that's a big red flag. We put everything out. We disclose everything. You want to cheat? You want to copy? Be my guest. You're going to have a great time, because we don't tell everything in here, but the basic idea is here. So calcium antimony is way down here. It's well below $100 a kilowatt hour. Everything. This is the price, not of just the electrodes, the electrolyte, but the entire battery with the battery management system, the power electronics, and so on. Okay, and this is calcium antimony data. Same thing, retention of nameplate capacity. All right, so where's Ambry today? It's been 12 years. It's hard to believe. If I were standing here in 2010 saying it was going to be at least 12 years, I'd say I'm not ready for such a long journey. No, we can't. This is tough tech. This is not like writing code. This is real. And upscaling, you'll hear tomorrow some of the obstacles that were in our path. But if we want to change the world, we have to have a product that's turnkey. Nobody wants to buy a battery kit. They want a ready, turnkey operation. That's been a long journey. It was just announced last month that Microsoft is the first customer. Microsoft is buying Ambry batteries to go with their solar-powered data centers, cloud computing, and so on. These people use huge amounts of electricity. And they could choose, they're Microsoft, they could choose anything. They obviously didn't choose lithium ion, they're far too smart for that. They didn't go for aqueous flow batteries, metal air batteries, all this other stuff. They chose this. With this, we're expanding our manufacturing facilities. We've been in Marlborough, Massachusetts, and we're moving about 20 kilometers to the south to a place called Milford, and be building out those facilities soon. And there's now people, it's funny, when you have a capital-intensive, risk-averse sector, nobody wants to be first. They're afraid of risk. Everybody wants to be first to be second. So once they see Microsoft go and say, oh, Microsoft's in, we're in. And so now they've got an order book of about $500 million. All kinds of people want to get. We don't have the manufacturing capacity because it's a chicken and egg situation. Why are we going to build out manufacturing capacity for orders that don't exist? So this is the problem when you're doing something for the first time. So anyway, things are looking good there. And there are joint ventures. As I said, we go local. And so with Reliance in India, a joint venture to manufacture Ambri batteries in India for the Indian market. And there's been interest from Saudi Arabia you might have read about the NEOM, this new city and so on. There'll be some manufacturing facilities there. And they are also interested in partnering to do this elsewhere. So I think that's probably a good place to stop and throw it open to questions. The only thing I would say is I hope I've given you some flavor for the thinking that led to this and sort of how difficult it is to innovate in this sector. And by the way, you know, we're publishing all these papers. You should see, you would think that a technology like this that the world needs, if somebody comes with a new idea, that you'd see bouquets of flowers and bowls of fruit. It's polar opposite. I mean, the stuff that we got thrown at us, just ad hominem stuff. It's a really vicious sector. But I was persistent and continued. And so at some point, we should get David Bradwell over here, because David, who's my first student, is the CTO, the Chief Technology Officer, and has been the steward of the upscaling. And I mean, no one was prepared for that journey. And so I salute all of the people on my team. Let's have some questions. Oh. Well, I'm heartened to see all these people here. Yeah.
What's the price of antimony?
The antimony price point is adequate to get us down below $100 a kilowatt hour when everything is done. And we've got facilities. There's antimony mines in all over North America. There's antimony mines in western U.S., out in Montana. There's antimony mines in Nova Scotia in Canada, and antimony mines in Mexico. So it's all North America. It's good.
Is it possible really to establish this on a very large scale? I mean, in terms of antimony that can be mined.
Oh, yes. Yes. So, I mean, I don't know going into the future, I mean, just how big, you know, how many gigawatts. I mean, if we're talking about terawatt hours, I can't answer that one. But we did make charts of Earth abundance and looking at if we wanted to make 1 gigawatt hour per year of liquid metal battery storage, which elements would make the cut and which ones lie below. And antimony lies above, so it's okay. Yeah. By the way, it's a funny story. You know, we did this work with lead antimony, which we wanted. We wanted the lead to give us the lower melting point without any loss in performance. And so I called the guy at the antimony facility in the western U.S., and I asked him for pricing. And he gives me a number, and I said, what about prices that vary with purity? How about low purity antimony? So what's the impurity in antimony? He says lead. Well, how about lead contaminated antimony? Oh, he says, oh, the price goes way, way down. Then I called a lead mine in Missouri, and the same thing. I said, well, how about lead? And he gives me a price. And I said, what about low purity lead? Yeah, so what's the main impurity in your lead? Antimony. I said, well, just give me that one. And the price goes down, 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 down. Because as scientists at the lab, we want to have the purest components go in. But when you're manufacturing, if what you want is antimony lead alloy, well then why would you buy high purity lead to get rid of the antimony and high purity antimony to get rid of the lead and then mix them? So there's all of these surprises that you learn.
Hang on for the mic.
For the feature of the batteries, there's a quite nice patent of Ambri, but it's very long. And my impression is the cheapest is maybe to use a simple steel housing, use alumina for the insulation and glass seal, but glass seal is not very stable with sodium. The most expensive would maybe aluminium nitride using some metal sealing and maybe nickel-based alloy for the housing, but this is extremely difficult to join. So my question would be, what is a correct best compromise?
You put your finger on the thing that was making it impossible to proceed with upscaling at Ambry. I showed you the schematic with the liquid metal on the top, and you see them all touching the wall. But you can't have that, because if the liquid metal on the top touches the wall, then it shorts to the liquid metal on the bottom. And we don't want to have to put an insulator inside. If we have to put a ceramic insulator, when I hear the word ceramic, I see dollar signs. They're expensive, they're fragile, they're brittle, and the metal on the top, axiomatically, it is the electropositive metal. It is, if I wanted to make aluminium from aluminium oxide, well, what would I use as a reducing agent? I'd go to the northwest part of the periodic table. So it's really hard. You're absolutely right, that with the lithium reacting and so on. So instead, we put a metal mesh, nickel metal mesh, and then by surface tension, the metal on the top is contained inside the liquid metal mesh and doesn't touch the sidewall. But that liquid metal mesh has to be connected to the outside world. So it has to go through the top of the cell, and it has to be hermetically sealed, and it can't be welded because now it's an electrical short. So it has to be dielectric, and Norbert has correctly said, is it an oxide? Well, it's going to be attacked by lithium. Is it a nitride? Yeah, we looked at nitrides, but then now you have ceramic metal bonding, and that's an entire field. And it has to be easy to do on an assembly line. And so this is a big challenge, but we've solved it. And again, I could have done it in 2010, gorgeous ceramics, but NASA price point, no good. It doesn't do you any good to have a $5 cell with a $100 seal. So we had to master all of that. How do we do it? I don't know how much of that I'm at liberty to disclose, but let's say Norbert has made some reference to nitrides. You know, lithium will react with oxides, but there are nitrides that are resistant to attack by lithium metal. Now that we've moved over to calcium, it's a different set of issues, but you have to have something that will not form a stable nitride. But you know, if we could use oxides, we would, but we're using nitrides, and then there's this whole graded seal so that you can, because you have to, well, remember, you start with this thing that's at room temperature and that's going up to 500 degrees Celsius. And the coefficient of thermal expansion has to be perfect, otherwise you'll get one's expanding more than the other. You can always take ceramics and you can stress them if they're in compression. So if the internal member is pushing on the ceramic collar, that's tolerable. But you can't have the inverse, where the collar is expanding more than the interior, and then you're going to get buckling and so on. So all of that stuff has to be engineered. So if you look at Ambry patents, there'll probably be some clues as to what it is. But I don't want to get spanked when I get back to Boston. They said, what are you doing telling people all of this stuff? Now's the time. You can ask anything. By the way, I never, as a teacher, I never make this statement. So are there any questions? Because there's two answers to that question. All right, well, look, if I want to give you body language that indicates that I don't want your questions, are there any questions? That means I don't want to talk to you, all right? So instead I say, now it's time for your questions. I invite your questions. Yes.
Since you're not looking at your watch.
Very interesting talk. So this is Abhishek from IIT Bombay. As you mentioned about making the battery from locally sourced materials. So I think it has taken a lot of effort to reach to a calcium antimony battery chemistry. But if we had to locally source the metal for each country or each region, then we have to start sort of all over again for that particular region. And there's a lot of effort which is required to be put by the local engineers and scientists. So, I mean, how do we sort that out?
Well, I think we don't just send a team in there to start exploring. I think at the early stages, in the case of India, for example, Reliance is going to be the partner. And as you know, Reliance is a formidable manufacturing firm. They're really big in things like industrial polymers and so on. So they're first going to have the geology sorted out so that they know what are the candidates, and then we can take a look at this is what's available and formulate according to what the local resources look like.
Okay, yeah, thank you.
Could you explain what happens to the Could you explain, please, what happens to the antimony over a decade or several decades? Can it be restored? And also, if you have time, what about antimony in other parts of the world?
Yeah. Okay, so first question is what about, I get sort of tantamount to end of life. I get this all the time, like, well, what happens at the end of life? So as you see, that there is no sort of progression to death by capacity fade. So we might freely go in there and say, out of an abundance of caution, maybe after, say, 20 years or 25 years, you know, the steel is in there, and you might say, well, maybe we should shut this thing down and put in some new steel and so on. So let's say we shut it down. So what happens? The steel can be recycled and go back to the electric arc furnace. The antimony can be taken out. It'll be a big puddle at the bottom. And that, if I wanted to reuse the antimony, I would purify it by electro-refining it, which is the same thing as charging the battery. The salt can be reused, and the whatever we're using on the top, whether it's lithium or calcium and so on. So we don't see a big disposal problem. And unlike lithium ion, where people are struggling today to try to recycle lithium ion, and to me it's a little bit like recycling polymers. It's easy to say the words, but in point of fact, a lot of those things are very, very difficult to recycle. So this we see as doable. Yeah. But you had a second question.
Other parts of the world.
Other parts of the world? I mean, we obviously know what's going on in North America. But beyond that, if antimony is a problem, no, we can run these things with lead, we can run them with zinc and a whole bunch of other things. And by the way, apropos of your question, so you say, well, yeah, but you just said lead was a low voltage metal. If you put lithium opposite lead, it's low voltage. Lithium opposite antimony is high voltage. Yeah, that's true. And ideally, you'd like a higher voltage. But in the end, there's only one metric that counts, and that's dollars per kilowatt hour per cycle. If I gave you a battery today, but people ask me, what about your round trip efficiency? It's about 80%, including the thermal penalty. So 20% of electricity is going into heat, but we still get 80%. 100 units goes in, 80 units comes out. So, oh yeah, but lithium ion is much higher. Yeah, but it catches fire and it costs about $500 a kilowatt hour. I don't know who's screaming at me. So, and then I can't believe this, but I've been to meetings, scientific meetings, and I won't name names, but people from institutions who should be ashamed of this, and they're giving a presentation about stationary storage, and they're quoting the energy per unit mass, like how many watt hours per kilogram. And I was at this one, it was an Electrochemical Society meeting, and Bob Huggins was there. He's probably 80 years old, from Stanford. And he attacked this speaker and he said, why are you quoting watt hours per kilogram? Are you planning on moving this thing? What's the matter with you? And so those are not useful metrics. And the other metric that isn't useful is the voltage. The only thing that counts, and by the way, the round trip efficiency. Suppose I told you I have a battery. I won't tell you the chemical composition. I have a battery. Its round trip efficiency is 35%. and its capital cost is $5 per kilowatt hour. Everybody in this room would buy that in battery and deploy it. The rest doesn't count. So, you know, you have to understand what the critical pieces are.
Okay. Take one last. Yeah, quick question, but we will have time at the end of today for a discussion and question sessions for any other questions that people may have.
Thank you. So in your talk, you use reduction cells as an inspiration. And I was wondering if you could give us an estimate how long it would take to get to that scale. And also, if it's really possible to get to that scale with the present design.
Yeah, so the reduction cell was the inspiration for massive consumption of electricity at high temperature. And I could go into all like the liquid metal molten salt, the kinetics, the exchange current densities. David measured the exchange current density on calcium was 600 amps per square centimeter, not 600 milliamps, 600 amperes per square centimeter. There's the polarization resistance. There's nothing at the activation over potential. It's just the ohmic drop across the electrolyte. So that was the inspiration. But, and I must confess, when I was young, working on this thing, I had this image that we could have a battery the size of this stage, and you know, no, you can't build that. It's too difficult to build because you have to have that foam on the top and balance it. If there's any non-uniformity, the current will short where the resistance is less. And we even tried. When I gave my TED talk, I showed we had the small one, which we called the shot glass, and then we had one that was I called it the hockey puck, because coming from Canada, it's 3 inches in diameter. And then we had the one, the bistro. We were talking about the pizza. It was 16 inches, 40 centimeters in diameter. It was 1,000 amp hour. No, it was 1 kilowatt hour in a single cell. And we had to have 3 current feed-throughs at the top to balance the current coming through. And the thing weighed about 150 kilograms, just the one cell. And we said, this is unmanageable. So then we took a step back, and the batteries say the size of a 40-foot shipping container, but the individual cells are about 100 amp hours, because you can get too big. So your question is correct. I mean, the answer is never. We will never have something the size of an aluminum cell as a single cell. The aluminum cell has multiple anodes, but one gigantic aluminum pool as the cathode. So we could try to do that, but we just found it to be unmanageable. And you know, to be able to manufacture that to the price point that we're trying to attain, I mean, it's been a 10-year journey. I don't want it to be a 10-decade journey, so we got to get moving. So, yeah. The inspiration was correct, but the realization came with some sobriety.